Hi guys, in this video we're going to talk about the difference between fusion and fission, and this one's going to be a little bit more focused for us. What do we need to know about for our purposes in this unit? So let's go ahead and get our Cornell paper out. So remember, up here is where you're going to put your name, class, and date, and we're going to fill in the topic. For Unit 9B, Objective 4, Fission and Fusion. So let's get our essential question here. What is the difference between fission and fusion? So that's what we're going to be talking about in this video here. We are also going to discuss the differences in terms of a lot of different things. What is it? What can it be used for? Advantages, disadvantages, that sort of thing. So we're gonna cover a lot here in this question. What is the difference between fission and fusion? So let's get started. Let's talk about fission first. Fission is when an atom breaks into smaller pieces. Remember in Unit 7 when we talked about the different kinds of chemical reactions, we actually talked about decomposition reactions where a compound broke into smaller pieces. Fission is kind of like decomposition. What you have is big pieces, there's a big piece, breaking into smaller pieces. And maybe they're the same piece, they're usually not the same piece. And sometimes other little tiny pieces also come off too. But the point is we have a big piece and now we have a small piece. So that's fission. So we'll scroll up a little bit and then we'll talk about fusion. Now fusion is actually the opposite of fission. When smaller pieces come together to form one larger atom. Fission and fusion are similar in that they involve atoms, especially when we're talking about nuclear fission and nuclear fusion. But they're kind of the opposite of each other. And remember I said that fission is like decomposition, where in decomposition we had a compound breaking into smaller pieces. And in fusion fusion is like synthesis, where we've got the two smaller pieces, they come together to make one larger piece. Now when we compare fusion and fission to chemical reactions, fission is like decomposition where a compound breaks up, and fusion is like synthesis where the two smaller pieces come together. In the reaction equations, they look like the opposite. Remember in decomposition, which I'll jot over here, we had A, B stuck together and then it broke down into A and B. And synthesis was the opposite, where you had A and B coming together to make A and B. It's going to look the same way here, except instead of compounds and atoms coming together or breaking apart, we're going to have the pieces of atoms coming together. So they're going to look like those nuclear reaction equations we watched in Objective 2. So let's talk about some facts about fission and fusion, and I'm going to flip over to the back side of this paper. And we all know how much I just love to make charts, so I'm going to split this in half. We'll put fusion on one side and fission on the other. Fusion, fission. And then we'll be able to talk about some things at the same time. Let's talk about energy first. And energy is an interesting thing to talk about with fission and fusion. So we're gonna start there. So now you might be surprised, and we'll talk a little bit more about this as we go here. Fusion releases energy, and so does fission, and that's going to seem a little confusing, but let me talk to you about that. So there's this weird thing that happens. You see, when we're talking about fusion, we're talking about the little pieces that come together to make the big piece, and we're talking about fission. We've got a big piece breaking apart into little pieces. Now, we don't talk about fission of little pieces. We don't talk about the fission of a hydrogen atom. The hydrogen atom is little bitty. It's not going to break up into little pieces. And we don't talk about the fusion of really big atoms either, because they're so big they don't stick together very well. So when we're talking about this, we're talking about big atoms breaking up for fission and little atoms coming together for fusion. So they would be the opposite if we used the wrong kind of particles, the wrong size of particles. But for our purposes, we're always releasing energy, and that's a good thing because we need energy in this world, don't we? So the next thing we'll talk about is how they're different in the way that they happen. So fusion happens when little pieces come together to make a big piece, and what's necessary for that to happen is high temperatures, like the sun. Fusion happens in the sun. It's a very high temperature, lots of gravitational forces pulling everything together, lots of pressure in there. This happens just fine on its own in the sun. Fusion does. Now, fission requires extra pieces. And what I mean by that is that often in order for fusion to happen, in order for it to break up into these little things, we have to take another little tiny particle and shoot it out there just to make it a little bit unstable. So fission, this is how it's different than radioactivity right here. Radioactivity just happens on its own. Fission, we start fission by adding some things. Now, a lot of times when fission happens, those little pieces sometimes send off some of these little extra pieces that get some more fission reactions going. And if it happens enough, if there's enough little particles coming out, you get something called a chain reaction. And chain reactions are incredibly useful in nuclear plants. Fission is what we're using in a nuclear plant to produce energy, and it works just like a coal plant, except it comes from the nucleus of atoms. Coal, we're burning fuels, and we use that burning fuels to heat up water. In a nuclear plant, we don't use burning fuels, we use radioactive elements, and we start fission happening, and that produces energy. Remember, up here it releases energy. And we use that to heat water, and after that it's the same. It's just where that heat comes from. So it would be really nice if we could use fusion, because fusion would result in fewer problems for us, but fusion requires such high temperatures that it costs more to do than it does to use. So I'm going to scroll down some here, like that. And draw another little line here so we can add some more. What we're going to talk about next is use in a nuclear plant in terms of the power that we're getting from it. And we're going to be looking at a couple of other things also. We're going to be looking for the good things and the bad things. I'm going to put plus for good and minus for bad. So we're going to talk about the good things that fusion and fission can do for us as far as nuclear power, and the bad things that nuclear power has as a result of that. So let's go ahead and start here. For starters, they are both more efficient than coal. In fact, there's some really awesome pictures you can look at on the internet of comparing the amount of fuel that you would need to power a home for a year. It takes like this tiny little piece, a kilogram of uranium, versus like truckloads and truckloads and truckloads of coal. So you get a lot more energy out of one little piece when you use fission or fusion. Fusion uses a gas, so we're talking about even something smaller there. Another advantage of fusion, but not fission, is that the fuel is everywhere. The fuel that we would use for a fusion reactor would be hydrogen, and hydrogen is literally everywhere in the universe. So even if we used spaceships or if we use this as power in a spaceship, when a spaceship gets somewhere and it runs out of power, it can just get some more hydrogen and keep on going. So that fuel is everywhere. The bad thing about fission or fusion, well, the bad thing about fusion is that it uses too much energy. And I'm going to add on here for now, because right now it uses a lot of energy, but in the future we might be able to figure out how to get this to happen with less energy requirements, and it's because it happens at very high temperatures, and in order to sustain something at that high enough of a temperature, it takes a lot of lasers and magnets, and it's just not feasible right now. So no nuclear plants actually use fusion as a power right now, but they all use fission. One of the drawbacks of fission is radioactive waste. You see, when we use these fuels to make a chain reaction take place, we end up with some radioactive materials left over, and right now they're just stored at the nuclear plants, and we've got to figure out what we're going to do with those, and they're still working on that. And unfortunately, politics is getting in the way now, so there's some trouble there, but it's not like it's leaking radioactive radiation out. You actually get more radiation from a coal plant, living next to a coal plant, than you do living next to a nuclear plant. Of course, you guys live next to both, being here in Columbia, because there's a nuclear plant over in Fulton. So that's all we really need to talk about as far as fission and fusion go. You should write a little summary here. And if you have any questions, make sure you ask your teacher. Thanks for watching.